This is the 2018 AQA AS Physics Paper 1. Question 1 asks us to describe the interactions responsible for keeping protons and neutrons together in a stable nucleus. We're also asked to include details of the properties of the interaction in your answer. So the force that keeps protons and neutrons together is a strong interaction. So obviously you need to know the types of interaction, the types of forces that are involved in nuclear physics. Now, because we're asked to provide some details of this property of the interaction, we need to talk about distances that applies across and things like that. So we can say that it has a short range. We can give some numbers linked with this. So we can say that less than 5 FM, it's an attraction. And we can also say that below 1 FM, it is a repulsion. We could also mention that it only affects hadrons, but it's a 3-mark question, so we've actually given 3 different points there. Part 2 says a nuclei can decay by alpha decay and beta decay. It says in alpha decay 1 particle is emitted, but in beta decay there are 2 emitted particles. Explain how the baryon number is conserved in alpha and beta decay. So we've got to talk about both, and we've got to specifically mention how the baryon number doesn't change even though we're emitting certain particles. Now, a lot of students found this question particularly tricky, and only about 11% of students got full marks. So if we start with alpha decay, we know that it emits a alpha particle which is 2 protons and 2 neutrons, but overall the number of protons before the emission and after stay the same, as does the number of neutrons. So what we can say is, even though these particles have been emitted, the number of nucleons is unchanged. I.e., the baryons in the parent nuclei equals the total number of baryons in the nucleus and alpha particle. So although there's the alpha particles being emitted, overall, if you compare the system before and afterwards, the number of baryons, the number of protons, the number of neutrons, actually stays the same. So if we look at now beta decay, so in this one we've got a neutron changing to a proton. So both of these, neutrons and the protons, have the same baryon number. So the baryon number remains unchanged. same. Now if we look at, let's say, the beta minus particle and the antineutrino, which is emitted, they have a 0 baryon number because they are both leptons. Which have 0 baryon number. So we've talked about all of the particles that have been emitted and what's happened to our nuclei after they've been emitted, and explained how and why the baryon number is left the same. Right, so part 3. We've got question: kaons are mesons that can be produced by the strong interaction between pions and protons. The equation shows a reaction in which a kaon and a lambda particle are produced. Deduce the quark structure of the delta zero. Okay, so what we need to do here is recall our quark structures. So if we write down these are the quark structures that you've really just got to learn from your texts. So we look at the quark structures for our pi minus. That is an anti-up and a down. Our proton is an up, up, down. So at the moment we've got our anti-up, a down, up, up, down on this side of the equation. Now we can say that the anti-up and the up, they annihilate each other. So if we get rid of the anti-up and the up, we're left on this side, on the pi minus proton side, with a down or two downs and an up. So on the other side we've got our kaon, and we know the kaon structure is a down and an anti-strange. So this takes account of one of our downs. So we're left with an up and a down on our interacting side. But if you see with the kaon, we've got an anti-strange. Now we know that strangeness is conserved because it's a strong interaction. We've been told it's a strong interaction, so we know that strangeness is conserved. So if we've got an anti-strange on the kaon, we must have a strange quark on the delta zero, so they cancel each other out, they annihilate each other. So we can say that that would have the up and the down that we had left over from this part of the structure, from the two particles interacting, and we must have a strange particle, so that annihilates, that interacts with the anti-strange from the kaon particle. So like any equation, we've got to balance both sides. So what we've got on the left hand side equals what we've got on the right hand side. So part 4 says the kaon decays by a weak interaction. The equation shows an example of kaon decay. State one feature of this decay that shows it's an example of the weak interaction. So we've already said that the K from the previous question, we know that the K naught is a down anti-strange. Okay, but we also know that the pi plus and the pi minus does not have any strange quarks. So pi plus pi minus, no strange quarks. Therefore, strangeness is not conserved. Therefore, it must be the weak interaction. Right, so the last part of this question, over 50% of students got 1 mark for it, so they were able to give 1 point. But only 5.3% actually got 2. So the question says there have been considerable advances in our understanding of particle physics over the past 100 years. Explain what's necessary for many teams of scientists and engineers to collaborate in order for these advances to be made. So our first point is to look at particle physics. We need lots and lots of different disciplines and different skills as engineers, as particle physicists, as mathematicians, etc. So for our first point, we could say that many skills and disciplines are required. So that would be our first marking point. But for our second, we could say that particle accelerators are expensive, so we need collaboration to spread the cost. We could also add ideas about there's lots of data to process, so we need many teams to analyze all these different data. And also the results of these experiments, once a team has analysed and come up with some ideas and published, they need to be peer reviewed. So therefore you need other groups to look at these data and comment on them and describe how valid they are before they can be accepted. So question 2 is a mechanics question where we've got a truck moving freely down a ramp inclined at an angle to the horizontal. We're told that the truck starts at the top of the ramp at point A. Friction and air resistance is negligible. As the truck moves down the ramp to point A, its centre of mass has a total vertical displacement of 8 meters. Calculate the speed of the truck at point A. Now, a lot of students during the exam tried to solve this problem using equations of motion, but the key here is to note that the loss in gravitational potential energy will be the same as the gain in kinetic energy at the bottom. So we end up with mgh, which is the gravitational potential it started with, will be converted to half mv squared. So we can cancel out the masses. So, and then if we rearrange this equation, we end up with half mv squared, half v squared equals g h. So if we plug in the numbers, we end up with half v squared equals 9.81 times by 8. So if we calculate that and then double it and take the square root, we end up with v equals 12.5, which equals 13 to two significant figures, which is the same as the raw data that we've been given in the question. Right, so it says figure 2 shows the truck moving down a ramp with a varying slope rather than the straight slope we had in the earlier question. The truck starts from rest and moves freely down the ramp. It reaches point C and then moves along the horizontal runway to D. Again, friction and air resistance are negligible. Discuss how the acceleration of the truck in figure 2 differs from the acceleration of the truck in figure 1. Now again, because we're asking about how it differs, it isn't just a case of talking about how the acceleration occurs in this figure. We've got to compare it with the previous one. So we can say that in figure 1, in our previous example, the acceleration was constant. Because the slope was straight and constant, therefore the contribution of gravity was going to be constant, and that's why we had constant acceleration. But in figure 2, because we've got a slope that starts off steep and then gets more shallow as it reaches C, we can say that in figure 2 the acceleration was greater at the top, and then the acceleration decreased as it got closer to C. Now note that it is still a positive acceleration. So we're still accelerating, but the actual magnitude of the acceleration is decreasing, but we've still got a positive acceleration. And then as we get between C and D, because we're now horizontal, then acceleration is going to be 0. So between C and D, the acceleration is 0 because there's no horizontal force exerted on the truck. So because there's no external horizontal force, then there's going to be no horizontal acceleration. Now, again, in that previous question, a lot of students, or some students, spoke about speed rather than acceleration. So again, it's worth making sure you understand what the question is actually asking for. So part 3, the total vertical displacement of the centre of mass of the truck in figure 2 is also 8 meters. So again, it starts from the same height. The speed of the truck when it reaches the horizontal runway is the same as the speed of the truck from figure 1 when it reaches A. Explain why. So because we spoke about in the first part of the question how all the gravitational potential energy was converted to kinetic energy, the truck started with the same gravitational potential energy because it was 8 meters above the where it ended up. So because the loss of gravitational potential energy is exactly the same, it doesn't matter how steep the slope was or whether it varied, like in figure 2, the loss of gravitational potential energy is exactly the same. So the gain in kinetic energy will be exactly the same. So the velocity increase will be the same. So we can say that the loss of gravitational potential energy is the same. Therefore, the gain in kinetic energy is the same. So only less than 20% of students scored this mark. But if you'd, in the first part, have realised that the question was all about loss of gravitational potential energy and conversion to kinetic, then this part of the question should have been straightforward. So this one, it says the horizontal runway in figure 2 has negligible friction and air resistance. As the truck moves along the runway, it starts to rain. The rain falls vertically and the water collects in the truck. Discuss whether there are any changes in the momentum of the truck and the collected water. So if we just draw a little diagram of the truck. So the truck is moving along like this, and it's moving in that direction. And as the rain starts to fall, it's falling vertically, and it starts to fill up the bottom of the truck. So initially, if we think about what's going on with the rain, initially the rain has momentum in the vertical direction, but no horizontal momentum. But once it's collected in the truck and it's moving in this direction, then the rainwater will have horizontal momentum. So if we just put that down first, so we can say that initially the rain has no horizontal momentum, but it does have vertical momentum, which is reduced once it reaches the truck. So we can say the vertical momentum is reduced. Okay, so there's no external horizontal force on the truck or the truck water combination system. So because there's no external force, then there'll be no change in the horizontal momentum of the system. Okay, but because the mass of the truck water system will start to increase as it fills up with rainwater, remember that momentum equals mass times velocity. So because the overall horizontal momentum of the system won't change because there's no external force, because mass is increasing, then the velocity must be decreasing. And as we stated before, originally the water didn't have a horizontal component, but now it's in the truck, it does. So the horizontal component of the water will increase, but the system as a whole, i.e. the truck and the water, doesn't change. So if the horizontal momentum of the water is increasing, that must mean that the horizontal component of the truck itself must be decreasing by the same amount that the water is increasing, because when they're both together, both added together, it will remain unchanged. So what we can say about that is there's no external horizontal force, on the truck water system. Therefore, no change in momentum of system. But the horizontal momentum of water increases so horizontal component of truck decreases by same amount. We can also say as momentum of system remains constant, due to the mass of the system increasing due to water, the velocity of the system must decrease. So question 3 shows us some energy levels for a hydrogen atom. So we can see how, as we go from one level to the next, because the energy is changing, we have an energy difference. So what I'll do now is just work out the energy differences for each of these gaps. So because we're starting here at the top at minus 0.85, then the next energy level is 1.5. The difference between these energy levels is 0.65. So if we do the same for the next two, we have an energy difference between 3 and 2 as 1.9, and the energy difference between 1 and 2 is 10.2. Okay, so we can see how the energy difference between the different levels increases as we go down. Okay, it says an excited hydrogen atom can emit photons of certain discrete frequencies. 3 possible transitions are shown in figure 3. So that's where we've got A, B and C. So part 1, the transitions shown in figure 3 result in photons being emitted in the UV, visible and infrared regions of the electromagnetic spectrum. To which region of the spectrum do the emitted photons belong? Okay, so we know that we've got in order, we've got UV, visible and infrared. So at this stage you might not remember which are the highest energy and which is the lowest, but visible is the central one. So we can see that in the diagram B is the central value of the energy level. So I think without sort of like knowing too much about the physics, we can certainly say that B represents the middle energy transference, which is visible. Now it's just remembering which is the higher energy and which is the lower. So we've got A, which is the lowest energy that's emitted. Now what you've got to recall, out of these three wavelengths, is infrared is the lowest energy and ultraviolet is the highest. So A represents infrared and C represents UV, because UV is the highest energy out of those three, and C represents the highest energy change out of those levels. Right, so two ways to excite a hydrogen atom are by collision with a free electron or by absorption of a photon. Explain why, for a particular transition, the photon must have an exact amount of energy, whereas the free electron only needs a minimum amount of kinetic energy. So what a lot of students tend to do is go straight into about the energy of the photon or the electron without explaining what's happening to that energy. So you've got to explain, what is going to happen to the energy of the photon or the electron. So what we can start by saying is energy is needed for the electron to move to a high level. Okay, so we're saying what's actually happening to the absorbed energy. And with electrons transition going to a high level, then for a transition to take place, an exact amount of energy is needed. So if the energy difference between two energy levels is, let's say, 0.9 electron volts, then it needs to absorb exactly 0.9. It can't absorb 0.8, it can't absorb 1 or 2, it's got to be that exact amount. So, and that's either coming from the photon or the free electron. But what we can say is when it interacts with a photon, all of the photon's energy is absorbed. So that's why, because it's absorbing all of the photon's energy, not just a bit of it, that's why the photon's energy has got to exactly match the energy difference between the levels. But an electron can transfer part of its energy and then continues with a lower kinetic energy. So the amount of kinetic energy difference between the electron initially, then after it's interacted, is the same as the difference in energy levels of where the electron has been excited to a different energy level. Okay, part 3. The surface of a sample of cesium is exposed to photons emitted in each of the three transitions shown in figure 3. The threshold frequency for cesium is 5.1 times by 10 to the 14 Hertz. determine whether any of these transitions will produce photons that will cause electrons to be emitted from the surface of cesium. So first off, the equation that we're going to use is work function equals hf naught, where f naught is the threshold frequency. So if we plug in the numbers, we've got Planck's constant, which is given in your equation sheet, which is 6.63 times by 10 to the minus 34, times by the threshold frequency, which we're given in the question, which is 5.1 times by 10 to the 14, and that comes out to be 3.38 times by 10 to the minus 19 joules. Now remember that in the previous figure, when we've got the energy levels, that's given in electron volts. So what we need to do is convert this number into electron volts by dividing by 1.6 times by 10 to the minus 19. So that energy now in electron volts will be 2.1133 electron volts. So now if we go back to the original diagram where we calculated the difference between the energy levels, we've got 0.65, 1.9 and 10.2. So our value of 2.11 electron volts, the only transition that's larger than is the final one. So it's only C that's possible. So it's only C that's possible as the gap 10.2 electron volts is larger than the work function. Okay, so it's only 10.2 volts that's larger than this 10.11, because the others are 1.9 and 0.65 electron volts, which are smaller than the work function. So these photons wouldn't have enough energy for the photoelectric effect. Therefore, photons don't have enough energy for electric effect. Okay, so the last part of this question also involves a calculation. So it says photons, each with energy 12.1 electron volts, are incident on the surface of the cesium sample. Calculate the maximum speed of electrons emitted from cesium. So what we know is the energy of the photon equals the work function plus the maximum kinetic energy. Okay, so if we rearrange this, we've got the kinetic energy equals the energy of the photon minus the work function. So we've been told that the energy of the photon is 12.1, so that's given in the question here. We'd calculated before in the previous part that the work function is 2.1133. So that's just the answer to the previous question. And that comes out to be 9.9867 electron volts. So we're going to have to convert this into joules for the next part of the calculation. So we just need to multiply this value here by 1.6 times by 10 to the minus 19 to convert into joules, which gives us an answer of 1.598 times by 10 to the minus 18 joules. So now we've got the energy, we can work out velocity just with the equation kinetic energy equals half mv squared. So we know that kinetic energy equals half mv squared. So if we just rearrange that, we end up with v equals root of 2 times by 1.598 times by 10 to the minus 18, which is the energy that we have just calculated, divided by the 9.11 times by 10 to the minus 31, which is all mass of an electron, and that comes out to the velocity equaling 1.9 times by 10 to the 6 meters per second. Question 4 shows a uniform beam supported by two light cables AB and AC, and they're attached to a single steel cable from a crane. The beam is stationary and in equilibrium. So we've got the angles that the bar is to the vertical, and we can see the points A, B and C. It says state two necessary conditions for the beam to be in equilibrium. So obviously it's not moving up or down, and one of the conditions that most students got was the resultant force equals 0, but it's also not rotating. So we've got to talk about moments. So the sum of clockwise moments equals the sum of anticlockwise moments. And this is the condition that a lot of students didn't get. So state what is meant by the centre of mass. Again, this is one of those definitions that are in your syllabus that you've just got to know. So this is the centre of mass is where the mass of the body can be considered to be concentrated. Now note it says centre of mass, so some students talked about weight here, so don't get your definitions mixed up. If it's asking for the centre of mass in the question, make sure you're talking about mass in your answer as well. Right, so This question is asking you to explain why the centre of mass of the beam in figure 4 must be vertically above A. So if we go back to the diagram, so we've got A, so saying that the centre of mass in the figure must be vertically below A, so in this vertical line somewhere, and we're asked why to explain that. So again, we've got to consider moments that really, and the fact it's in equilibrium and it's not rotating. So we can say that so there is not a resultant moment about A because A is a pivot, so the line, so if the line of action has got to go through A, so you've not got any resultant moment to rotate it either clockwise or anti-clockwise, because A is a pivot, the line of action of forces pass through A. So only 2.9% of students got both marks for this question. So part 4 involves a calculation. Now we know that this system is in equilibrium, so we can use a triangle of forces. So we're told that the weight of the beam is 12,000 newtons, and so we know that the 12,000 newtons acts directly downwards. So this is 12,000 newtons. Now if we go back to our diagram, we're told that this is T1 and that's 53 degrees to the vertical, and this is T2. So along with our weight that's acting directly downwards, and we've got tension in that direction and tension in this direction, because it's in equilibrium, we know that the tension 1 plus the tension 2 must equal up to the weight downwards. So if we go back to our drawing, we've got 12,000 acting down, we've got T1 acting in this direction, and we know that this is 53 degrees to the vertical, and then we've got T2 acting in this direction, and this is a right angled. So we've got a right angled triangle with the weight, the 12,000, as our hypotenuse. So now we can just resolve the different forces. So we can say that T1 equals the 12,000 cos 53. So remember, SOHCAHTOA, cos is adjacent over hypotenuse, so we're just rearranging that so to get to isolate T1. So we can say T1, when we do that calculation, equals 7221 or 7200 newtons to the correct significant figures. T2 is 12,000 sine 53. Again, using SOHCAHTOA in this case, sine is opposite over hypotenuse. So this is our angle of 53. This is our opposite side, and the 12,000 is our hypotenuse. So T2 becomes, to two significant figures, 9600 newtons. So the last part of this question is asking us about Young's modulus. So it says a steel cable from the crane has a circular cross section of diameter 1.5 times 10 to the minus 2, and the cable is 12 meters long. It says calculate the extension of the cable caused by the weight of the beam. You can assume all the weights of all the cables are negligible, and Young's modulus of steel is 2 times by 10 to the 11 pascals. So we're going to use the equation of Young's modulus equals the force times by the length divided by the area over the extension. So the first thing we've got to do is work out this area, the cross-sectional area. So we know that A equals pi r squared. Now don't forget, we've been given the diameter, but the equation for area means that we're going to have this as the radius, which some students forgot to convert. So this is 0.75 times by 10 to the minus 2, and that's going to be squared, and that comes out to be 1.767 times by 10 to the minus 4. So then if we rearrange this equation and plug in the numbers, we get delta L, so our extension, is our force, which is 12,000, times by our length, which is 12 meters, divided by our area, which we've just worked out to be 1.767 times by 10 to the minus 4, times by Young's modulus, which is 2 times by 10 to the 11, and that comes out to be so the extension comes out to be 4.1 times by 10 to the minus 3. Question 5 is a question about density. It says calculate the weight of an ice cube that has a volume of 4 times by 10 to the minus 6, and we're given the density of ice as 920. So we know that density equals mass divided by volume. So if we rearrange this, then mass equals density times by volume. So we're asked to calculate a weight. So to calculate a weight, we first got to know its mass. So if we put in the values that we know that the volume and the density for this ice. So the density is 920 and the volume is 4 times by 10 to the minus 6. So the mass comes out to be 3.68 times by 10 to the minus 3. Now once we have mass, we can work out its weight by multiplying by gravity. So the weight is going to be 3.68 times by 10 to the minus 3 times by 9.81 for gravity, and that comes out to be 3.6 times by 10 to the minus 2 newtons. So figure 5 shows the ice cube floating in a beaker of water. It says when the ice cube is placed in the beaker, it displaces a volume of water, causing the water level to rise. The weight of water displaced is equal to the weight of the ice cube. Calculate the volume of water displaced by the ice cube, and we're given the density of water. So we've already just calculated the weight of the ice cube in the previous question. So we know that the weight, so if we know that the weight of the ice cube is 3.6 times by 10 to the minus 2, then we know that the weight of the water displaced is 3.6 times by 10 to the minus 2. But we're going to have to convert this to mass, because what we're going to be doing, because we want to calculate volume, we're going to have to be using that equation of density equals mass divided by volume again. So we've got to convert the weight back to a mass by dividing by gravity. So the mass of the water displaced is the 3.6 times by 10 to the minus 2, which is the weight that we got in the previous answer, divided by 9.81, which comes out to be 3.68 times by 10 to the minus 3. And we know that volume equals mass divided by density. So the volume of the water displaced, now we know the mass, which is this, is 3.68 times by 10 to the minus 3 divided by the density of water, which is 1,000, which were given in the question. So that comes out to be 3.7 times by 10 to the minus 6 cubic meters, to two significant figures. So again, we're given some of this information, the previous one, i.e. the weight of the ice cube. We're told in the question that the weight of the water displaced is the same as the weight of the ice cube. So it's just a matter again of using this equation here once we've converted the weight to a mass. So question 5.3, it says the ice cube in figure 5 is replaced by another cube, also of volume 4 times by 10 to the minus 6. This cube's made of ice containing a small piece of iron. The mass of the water now displaced is 3.9 times by 10 to the minus 3. And it says calculate the volume of the piece of iron, and this is the density of iron. So it's helpful if we draw a picture of this cube. So basically this is the cube, and inside it is a piece of iron. Okay, so the volume of the full thing is 4 times by 10 to the minus 6. This has a particular volume which we'll call V. So the amount of ice is 4, so the ice will be the 4 times by 10 to the minus 6 minus V. Okay, and the weight of the water displaced will be the weight of the ice plus the weight of the iron. So the weight of H2O displaced will be the weight of the full thing. So that's the weight of the ice in this cube plus the weight of iron. Okay, so let's start looking at the numbers of this. So we've been told that the mass of the water now displaced is 3.9 times by 10 to the minus 3. So that's going to be made up of the mass of the iron, which will be V times by 7800. So remember, V is what we're calling the volume of the iron, multiplied by the density of the iron. So that will give us the mass of the iron that's in this cube. If we add that to 4 times by 10 to the minus 6 minus V, which is the volume of the ice in this cube, and then multiply that by 920, which is our density of ice, that will give us the mass of ice in this cube, and that will all equal 3.9 times by 10 to the minus 3, which we're told is the mass of the water which has now been displaced, i.e. the mass of this full cube. So if we do some rearranging of this, we've got 6880V equals 3.9 times by 10 to the minus 3 minus 3.68 times by 10 to the minus 3. So all I've done here is multiplied out the brackets and then rearranged. So we end up with V equal to 3.2 times by 10 to the minus 8 cubic meters. So that will be the volume of the iron in this cube. Question 6 gives us a circuit diagram. So it says a student connects 4 lamps A, B, C and D in the circuit shown in figure 6. The battery has an EMF of 9 volts and negligible internal resistance. So we've got A and B on the top spur and C and D on the bottom spur. Part 1 says we've got a table here, and that shows the operating conditions for the lamps when they are at normal brightness. Okay, so this is when they're at normal brightness. So we're told at normal brightness the operating voltage of A and C, which are identical, is 6 volts and the power is 6 watts. And B and D, which again are identical, has an operating voltage of 3.5 volts and a power of 4.1. The student observes that 2 of the lamps are at their normal brightness. Assume that any changes in resistance of the lamps are negligible. Determine which 2 lamps are at their normal brightness. Use calculations to support your answer. So the first thing we need to do here is work out the resistance of each lamp. So to do that, we're given voltage and power. So to find resistance, we're going to use the equation R equals V squared over P. And if we do that, if we just plug these numbers in, we get the resistance of A and C to be 6 ohms and B and D to be 3 ohms. So we know that the voltage is going to be split in each spur to the ratio of 6 and 3 because one of the spurs has A and B and the other one has C and D. So the potential difference across B and D is going to be 3 volts because that has 3 ohms, so then the 9 volts as I said, are going to be split in the ratio of 6 and 3, because the total of these together is 9 ohms. And the potential difference between across A and C is going to be 6 volts. So obviously you've got 3 volts across B and 6 volts across A. That's all 9 volts that comes from the battery. So we're told that A and C has an operating voltage of 6 volts, which is what we've got with the potential difference across A and C. But we've only got 3 volts across B and D, where its operating voltage would be 3.5 volts. So that means that A and C would be at normal brightness. Because the voltage across those two bulbs is the same as its operating voltage, where the potential difference across B and D is less than the operating voltage. So now if we look at 6.2, we've got the same circuit diagram, but a student connects another lamp E in the circuit as shown in figure 7. Lamp E is identical to A and C. So if we just have a look again at what A and C was. So A and C was 6 ohms. So if I just draw that onto the diagram, we've got 6 ohms here, 6 ohms here. So E we know is 6 ohms. Then the other two are 3 ohms each. Okay, now I think a lot of students found this question really tricky. In fact, only 78% of the students actually scored 0. And the trick with this question is to realise that the top spur is identical to the bottom spur. So these two are identical. So the potential difference at this point here between A and B is going to be the same as the potential difference at this point here between C and D. So because this point and this point are identical, then the potential difference across these 2 points is going to be 0, and therefore no current is going to flow between these 2 points because the potential difference is the same. So if no current flows between this point and this point, then E will remain unlit and we won't have any change in the current going through A and B and C and D. So if we just write those points down, so we can say that the PD across the new lamp equals 0, therefore no current in E, and the other lamps are not affected because the current in the lamps does not change. 6.3 tells us that lamp B in the previous figure fails, so it no longer conducts electricity, and this change does not affect the resistance of the other lamps. Deduce the effect on the current in the battery and use calculations to support your answer. So a lot of students found this difficult, and 22% of students didn't even attempt the question. So if we just have to start by drawing the circuit diagram so we can see what's going on. So we'll start with bulb A and bulb C like we had before. Now we've got bulb E here. Now because we've got a bulb failure in lamp B, we're not going to draw that part of the circuit, so we're just going to go on to D and then carry on. Now I hope you can see that A and E are now in a series circuit, and that part of the circuit is parallel to C. So if I redraw that, we've got C underneath, and we've got A and E here, and then that goes off to D. So if I just write on the resistance as well, we know that that is 6, that is 6, C is 6, and D is 3. So the combined resistance for this spur is going to be 12 ohms because these two bulbs are in series. This spur is going to be 6, and then of course this is 3. So what I'm going to do is find the total resistance for this spur here and this spur here. So our total for this part of the circuit is going to be 1 over RT equals 1 over 6 ohm from the bottom spur and plus 1 over 12, which is the resistance from the top spur, and that comes out to be 0.25. So RT for that part of the circuit is going to be 4 ohms. So this part here is 4 ohms, and that is in series with this bulb D. So the entire resistance for the circuit is going to be the 4 ohms from where we've got the two spurs plus 3, which is bulb D. So that's going to come to 7 ohms. So now we know the entire resistance for the circuit now, then we can work out the current, because we know the PD from the battery is 9 volts. So the current equals V over R. So that equals 9 over 7, which is going to be 1.3 amps to two significant figures. Now from our previous circuit, where we didn't have any bulb failure, there was 9 ohms on each spur. So the total resistance for where we've got the two parallel bits of the circuit is going to be 4.5 ohms, because it's just again using 1 over RT equals 1 over 9 plus 1 over 9. And So the R total would equal 4.5 ohms. So this is for the original. So again, using I equals V over I, so this time I equals, the voltage would be the same, which is 9 volts, but this time the original circuit, the total resistance was 4.5, so that equals 2 amps. So we can see that compared to the original circuit, the current through the battery decreases. So we can say, therefore, the current in battery decreases after lamp failure. Question 7 gives us a figure that shows a diagram of apparatus used to demonstrate the formation of interference fringes using a white light source in a darkened room. Light from the source passes through a single slit, then through two narrow slits, S1 and S2, and we've got a distance D to the white screen there. And we've got the distance between the slits as S. Describe the interference pattern that can be seen on the white screen. So because we're using white light, then what we're going to end up with is, to begin with, we're going to have a central white fringe. So we get a central white fringe. Now we're going to get fringes either side of this, but that's going to be a spectrum of colours. So we're going to end up with fringes either side, and that's going to show a spectrum with red furthest away and violet closest to the centre. So 7.2 says a filter that transmits only green light of wavelength lambda and red light of wavelength 1.2 lambda. This filter is placed between the light source and the single slit. Describe the interference pattern now seen on the white screen. Use a calculation to support your answer. So in the central fringe, like before where we had all the colours, and that's why we had a white fringe, well here we're going to get the white fringe that's going to be a mixture of the red and green light. Now we know that we're going to get fringes either side, but with this it's asking for calculations, so it wants us to use that information about lambda and 1.2 lambda to give some description of the fringe spacing. Now we know that lambda is proportional to the fringe spacing, so if the green, therefore if the green fringe spacing is W and we increase lambda by 1.2, which we're given in the question, then W for the red wavelength is going to also increase by 1.2 because wavelength and fringe spacing are directly proportional. So what we can put as our answer, we can say that the central fringe will be a mixture of red and green light. We're going to have red and green fringes either side. And the spacing of the red fringes is 20%, i.e. 1.2 times greater than the green fringes. Part 7.3 tells us a student decides to use the apparatus shown in figure 8 to determine the wavelength of red light using a filter that transmits only red light. They suggest that if you decreasing the slit separation and decreasing D, the distance between the slits and the screen, the student decides to make each change independently. Discuss the effects of each independent change has on the interference pattern and whether this change is likely to reduce the uncertainty in the determination of wavelength. So there's a few things we've got to talk about. So we've got to talk about slit separation and we've got to talk about the distance to the screen. Now we can talk about those separately, but we also need to talk about how this changes the interference pattern and then how that change in the interference pattern affects the uncertainty in the determination of the wavelength. So if we take slit separation first, okay, so if we decrease the slit separation, then what the effect that has is the fringe separation increases. So because the fringe separation increases, there's a greater distance between them. So what that means is the uncertainty in the measurement of the fringe decreases because the bigger the distance that you're measuring, then the less uncertainty that there is. So the measurement of the fringe separation decreases. And because we need to know this measurement to calculate lambda, then if the measurement of the fringe separation decreases, then the calculation of lambda, the uncertainty of that will also decrease. So we can say as this is needed for lambda calculation, then uncertainty in lambda measurement will decrease. So the key thing to remember is if you are measuring a big distance, then there's less uncertainty in that. So for example, if you're measuring something that's a meter, then just by being a couple of millimeters out doesn't have as big an effect on your final result as if you're measuring something that's a centimeter and you're a few millimeters out, because the percentage error will be less with the bigger distance. So now let's turn our attention to decreasing D. Okay, so as we said before, if you're going to measure smaller distances, then the uncertainty is going to increase. So the uncertainty in measuring D will increase. But also, by decreasing D, the fringe separation will also decrease. Therefore, the uncertainty in fringe separation increases. We need both of these values, we need D and the fringe separation, to calculate lambda. So because the uncertainty in both these values will have increased, then that's going to increase the uncertainty of our lambda calculation. So we can say that as both values required for lambda calculation then uncertainty in finding lambda will increase. So the way that this was marked, it was in different sections, so you could either get 1 or 2, 3 or 4, or 5 or 6, depending on the quality of the answer. Now only 3.5% of students got into that top bracket of 5 or 6 marks, and this was mostly due to not explaining how the change in the fringe spacing affected the determination of lambda.